Hi, my name is Monet Roberts, and I will be participating in Challenge 2009, and I will be briefly discussing the pre-calculus concept of continuity. Now, as we ignore this nice Georgia Tech background, continuity has a definition. It has three conditions of this definition. The first, f of c must exist. The second is, as limit of x approaches this value of c of f of x, that also must exist. By these two conditions being true, the last one, the limit of x as it approaches c of f of x must equal f of c. Just as north has south, east has west, and up has down, continuity has the opposite, which is discontinuity. Many discontinuities, there are four. The first one is jump discontinuity, which occurs with a break in the curve. Right here, as shown in this graph, as the limit of x approaches 1 from the left side, that value is 1. As the limit approaches from the right side, it equals 4. There's a break in the graph, therefore making the limit as x approaches 1 of f of x non-existent. The second discontinuity is point discontinuity. It's when the curve has a hole because the function value is off of the curve, therefore making the limit as x approaches a of f of x not equal to f of a. As seen on the graph, as the limit of x approaches 3, there's a hole, and that value is at 1. But the f of 3, which is a filled in circle, is equal to 2, therefore making the limit of f of x as x approaches 3 not equal to f of 3. The third one is essential discontinuity, when the curve has a vertical asymptote, or VA. As shown on this graph here, as the limit of f of x as x approaches 2 from the left side is negative infinity because of the vertical asymptote and the way the curve is going downward, but does not have a specific value. And the limit of f of x as x approaches 2 from the right side equals infinity because of the upward sloping curve which goes up, therefore not really determining a value because the limit is really non-existent. And the last discontinuity is removable, which is when you have a rational expression with common factors in the numerator and the denominator. Let's look at an example. The example of limit of x squared minus 3x plus 2 all over x minus 1 as x approaches 1. Now, you can factor this problem to make it easy because you know if you put 1 in, there'll be 0 in the denominator, and that will make the function non-existent. You can factor it out, x minus 1 times the group, you can group them, which is x minus 2, which is the next one, all over x minus 1. You can cancel x minus 1 from the numerator and the denominator out, thereby making the function continuous because now you have x minus 2 and then you can plug in 1, thereby making the f of 1 equal to negative 1. Thereby making x minus 1 a removable discontinuity because you canceled those out. Let's look at it on a graph. Now you see that at x equals 1, there's a hole there, but the value is at x is at negative 1 because you plugged in 1 in the continuous function which gave you negative 1. But there's a hole, thereby making it a removable discontinuity. Let's look at some examples of continuity now that we looked at some examples of some graphs with the removable discontinuities. Example 1 is the function f of x equals x squared plus 3x plus 5 if x is less than 1, and 6x plus 3 if x is greater than or equal to 1, continuous at x equals 1. Now remember your three conditions. Now let's go through them slowly. A. F of 1 is defined because of the greater than or equal to sign, thereby making it x equals 9 because you plug in 1 in 6x plus 3 and you get 9. The second one, you have to find the limit as x approaches 1. Because x is less than 1, that will make it the left side of 1, which is x squared plus 3x plus 5. You plug in the 1 in the x and it equals 9. Because 6x plus 3 is x greater than 1, that means it's going on the right side. So it's 6x plus 3, and you plug in 1, and you get 9 also. Therefore, making the limit of f of x as x approaches 1 equal to 9. And now you have to test the last condition. The limit of f of x as x approaches 1 equals 9, and also the f of 1 equals 9, thereby making the conditions all true, and this function is continuous at x equals 1. Now let's look at another example. Is the function f of x equals 5x plus 7 if x is less than 3, 7x plus 1 if x is greater than 3, continuous at x equals 3? Let's go through our conditions one more time. A, f of 3 is not defined because you don't have anything that says that there's a specific value if x is equal to 3. But let's go ahead, and we cannot really plug these two in and determine whether if it's defined or not. So we have to test the limit, which is our second condition. The limit is of 5x plus 7 as x approaches 3 from the left side, because x is less than 3, equals 22, because you plug in 5 times 3 plus 7, which equals 22. The right side limit is limit of 7x plus 1 as x approaches from the right side, because x is greater than 3, equals 8. 22 and 8, of course, as us Georgia Tech students should know, does not equal. Therefore, the limit as x approaches 3, forget that little sign, as x approaches 3 does not exist, which means this function is not continuous. That is my discussion on continuity. I hope you enjoyed. Thank you.